Okay, so we have taken a look at the int and float numeric data types, and we have taken a look at 5 of the arithmetic operators, namely the double star exponentiation, which has the highest precedence, but unlike the others associates from right to left. Then the multiplication and division, star and slash, which associate from left to right. And then the lowest precedence of these 5 operators are the plus and minus, addition and subtraction, which also associate left to right. And of course we can use the parentheses to override or clarify precedence and associativity. Next we're going to take a look at a couple of string operators that we can use. So here I'm first of all creating a stir object. S is referring to this stir, the string, ABC underscore. Okay, so there's the value of S. The plus symbol, which of course means addition for numbers, for strings means concatenation. So if I say S plus some string like DEF, here I've chosen to use double quotes rather than single quotes. It really doesn't matter. What I get is a string that is the concatenation of the value that S refers to with DEF tacked on the end. Now this hasn't actually changed S. It's just produced a value, which is the value of S with DEF concatenated. Likewise, the star operator, or similarly, the star operator, which means multiplication for numbers, for strings means repetition. So S times 4, or S star 4, is S repeated 4 times with no gaps. So we have ABC underscore repeated 4 times as a single string. Again, this did not change S. The bool data type only has 2 legal values. There's true with a capital T, false with a capital F. And that's it. If you mistype the notation for true or false, Python assumes that you're attempting to refer to some variable for some object, and here I'm told that true with a lowercase t is a name that has not been defined. All right, so if you type an expression, that's a statement. If you type a variable name and a value, that's a Python statement. If you call a function like print, that's a statement. It turns out that a statement in Python has to be contained on a single so-called logical line. All of the statements that we've been doing so far have been statements on single physical lines. Okay, so a physical line is any line ending with a new line character. So when I say 12 times 23 and press enter, that is an expression statement ending with a new line, and it computes to 276. Likewise, if I say x gets 12, this is an assignment statement. When I hit the enter key, that creates both a physical line and a logical line. All right, so this distinction between physical lines and logical lines may seem a little strange. But it turns out that you're permitted to have long logical lines by continuing logical lines across multiple physical lines. If I simply say, let's suppose I wanted to set x to the value of some long expression. I might try to say something like x gets, and then press the enter key to continue my long expression on the next line down. But Python is not happy about this. Python is happy if I say x gets, and then press a backslash, and now I can continue my logical line on the next physical line down. And I'm just going to do some arithmetic here. Okay, so x now contains the value of that expression. Another way of continuing a logical line across multiple physical lines is to use parentheses to contain whatever value you want to express as a single within a single logical line. So here, again, I have some long expression. I'm using a parenthesis to begin the expression. And because I use the parenthesis, Python is happy for me to continue on the next line down. In fact, I can keep going until I press a closing parenthesis, and you'll notice that the idle interactive shell flashes to show me that I have closed the parentheses, and I press enter, and I've successfully, once again, created a single statement on one logical lines split across 5 physical lines. Okay, now just as you can split a logical line across multiple physical lines in this way, either using the backslash continuation character or by enclosing in parentheses, you can also, it turns out, have multiple logical lines within one physical line. And you do that by using the semicolon character. You may recall seeing the semicolon character as the statement terminator character in languages like C or C++ or Java. Here, the semicolon is a statement separator that allows you to give multiple logical lines on a single physical line. All right, so here on a single physical line, I've given the 3 logical lines with the statements x gets 14, followed by square root of x gets x to the 0.5 power, followed by x squared gets x to the 2 power. X squared gets x squared. And so now I have x, and I have square root of x, and I have x squared created on a single physical line. Frankly, this is not very often used because it can make code compressed and difficult for people to read. So generally speaking, people stick with the idea of having one logical line per physical line, or if necessary, having a logical line split across multiple physical lines, either using the backslash or parentheses. By the way, we're going to discover later that we can also use the square brackets or the curly braces to specify or to split things across multiple physical lines as well. Now, another important concept to understand is something called a compound statement. A compound statement is at least one and possibly more statements on separate logical lines. And compound statements come up in several contexts. For example, the body of a function, in the definition of a function, the body of the function is very frequently multiple statements long. Also, if you define a loop or a decision, which we'll start looking at in a little bit here, the collection of statements within that loop or decision, called the block of statements, is another example of a compound statement. And when we get into Financial Computing 1 and start talking about class definitions, that is our own user-defined types with strict interfaces and access methods we can call, and so on. These method definitions are also compound statements. All right, so there are many situations where these will show up, and let's look first at defining a function, because of course functions are very handy to have, and also this gives me a chance to illustrate the idea of using a compound statement. So here is what a very simple function definition looks like. In full, function definitions are more complex than this, but we're going to start out looking at very simple things. Def is a keyword that introduces the definition of a function. Then function name is like a variable name. It's a name that you make up that makes sense for your function, and the rules for function names are the same as the rules for variable names. That is, the first character has to be either a letter or an underscore. Following characters, if any, can be letters, underscores, or base 10 digits between 0 and 9. Now, after you give the function name that you want, you are required to have a pair of parentheses containing the so-called parameters that the function expects to receive. It's possible that the function does not expect to receive any parameters, in which case the parentheses might be empty rather than containing parameter names. But the parentheses are nevertheless required, so you always have to have parentheses when you define a function. And then finally, the definition of the function has to conclude on that same logical line with a colon. And when you're getting used to Python to begin with, forgetting that colon is going to be a very common mistake to make. Now, between the parentheses, you may have one or more so-called positional parameters. And these are variables that receive values passed in when the function is called. Notice that the statement within the body of the function has to be indented. There has to be at least one statement. The statement has to be indented, and in fact, there can be multiple statements, as indicated by the ellipsis here. And if there are multiple statements making up the compound statement that's the body of this function, then Python is very picky that all of these statements have to be at exactly the same level of indentation. Python uses indentation to keep track of which statements are within the function, which statements are after the function, and so on. Finally, you may have a return statement within the function that returns a particular value back to whoever called the function. If you don't specify an explicit return value, what you get back by default is none. For example, we saw that the print function returns none. It doesn't return a particular value. All right, so this is all very theoretical. Let's take a look at a specific example now. This one is simple. We're going to say define print pow, print underscore pow. And print pow is going to take two positional parameters, x and y. We could have used any variable names that we wanted. And what the print pow function is going to do is to simply print the value of the first parameter raised to the power of the second parameter. So x to the power of y. This function, you will notice, okay, now to persuade the interactive shell that I'm done defining the function, rather than continuing typing more statements, I'm going to type a blank line, and now the shell understands, oh, okay, this function body only had one single statement in it. This function is now correctly defined. And to call this function, I give the name of the function and two arguments. Now, notice that my interactive shell in idle is slightly clever. It tells me, oh, printPow wants to receive two arguments that will be stored into these parameters x and y. So I'm going to say 2, 3, and that's going to compute 2 cubed, which is 8. Or if I say print pow 3 comma 4, that's going to be 3 to the 4th, which is 9 squared is 81, and so forth. Now, print pow is not restricted to only working with ints. I can also use floats. So here's the square root of 123.5. It's important to understand that this value is not being returned by printpow. This value is being displayed by printpow by calling the print function. Here we have a very slightly different function called retpow that returns the value of x to the y power rather than printing the value of x to the y power. So I'm saying def retpow, and then in parentheses my 2 parameter names. It's typical to use xy or ijk or whatever. This time, instead of using the print function to display the result to the user, I'm going to return the computed result. And that will leave it up to the caller to decide what the caller wants to do with that value. So if I now say retpow 7 comma 2 as my arguments. Interesting. Okay, so I said retpow returns that value rather than displaying the value, and yet the value is being displayed for some reason. Well, what's going on here? What's happening here is that, remember that when you, at the interactive shell, give a value, the interactive shell displays the value. And that's true if you do a constant like 1234. It's true if you do an arithmetic expression like 1 plus 2. It also happens to be true if you do a function call of a function that returns some specific value other than none. So retpow is in fact computing and returning 7 squared, which is 49, and the default behavior of the interactive shell is to simply display that value out on the screen. Now, if I were to say x, well, let me choose a different variable name. So let's use w just to differentiate from x and y. So if I say w gets retpow of 7 comma 2, nothing is displayed on the screen here because the value that retpow returned is stored as the value that variable w refers to. Now if I ask to display the value that w refers to, now I see 49. With printpow, if I had said, let's say v, different name again, if I had said v gets printpow of 2 comma 3, interesting. Okay, printpow is displaying the 8. Well, that makes sense because printpow is actually calling the print function. I didn't get an error when I said v gets printpow, and the reason for that is that because printpow does not explicitly have a return statement in it, it gives me none by default. And if I want to see none, I have to use the print function to display none. Okay, so we can have functions that do not explicitly return a value, in which case they return none by default. And we can have functions that do explicitly return a value, such as retpow here, which returns the result of a computation. Okay, so retpow of 4 cubed is 64. Okay. Notice that it's pretty awkward defining functions in the interactive shell, especially if the functions are very long. Now, if the function is only a couple of lines long, that's okay. And that's reasonable to type. And in fact, idle's interactive shell gives me the indentation automatically. So if I say def foo1, this time I'm going to define foo1 not to receive any parameters at all. Notice that idle's interactive shell automatically gave me indentation. But if I mistakenly removed that indentation and said something like print foo1 has been called and hit enter, now I get yelled at because I forgot my indentation. Likewise, if I got the indentation just a little bit incorrect, like if I had one statement indented one extra space or one fewer spaces, Python would yell at me. So it's a lot more convenient for me to define functions and put test cases in program files. So let's take a look at this program file that we had before. All right, so that was prog1. I want to make sure that I have saved that, and I'm now going to create a new file containing the code for funtest.py as shown here on slide 40. So I'm going to start typing this in, and I will not force you to watch me type. Okay, so I'm just typing the last couple of characters here, and all right, now I've got my code typed in, and I'm going to say file save as. Okay, I don't want to overwrite prog1, so I'm going to type fun test. And again, that will automatically have a .py extension added on the end. So I now have this fun test program, and as we saw before, I can say run module, and I get my output. Now let's compare the output in the shell window with the version of the program on slide 40 on the left. I've defined printpal, I've defined retpal, I've called printpal with the arguments 2 and 3. Well, that's going to display 2 cubed, which is 8. So we did correctly get 8 displayed. Printpal 3, 4 is going to display 9 squared is 81. So I do get 81 correctly displayed. If I just call retpal 7, 2 within the program like this, unlike the interactive shell, nothing is going to be displayed. Okay, so within a program file, if I want to see any output, I must use the print function to display that output. So I will establish a variable. I'm using the name R here in the program. R is going to get the return value from retpal, and then I'm printing R, which is 7 squared is 49. So that's correct. Rather than using an intermediate variable like R, since retpal itself returns a value, I can do what's called nested function calls. If I say print retpal 4, 3, the inner function retpal is called first. It computes 4 cubed is 16 times 4 is 64, and that value 64 is then passed to the print function call and is displayed on my screen. Okay, so I have successfully created and tested and amazingly not made too many typing mistakes along the way of this funtest.py program file. Okay, so we have now pretty well taken care of variables, functions, arithmetic, low-level data types. Next, we want to be able to compare values to each other so that we can do things like making decisions, if-else decisions, or loops. So here are various comparison and logical operators. There are a few that are not shown in this table, but this is enough to get us going. It turns out that all of the direct comparison operators in Python have exactly the same precedence. This is not the same as, for example, C++ or Java. The double equal sign is the is equal to test. Exclamation mark equal is the is not equal to test. And then we have the not very mysterious less than or equal, greater than or equal tests. We can, of course, use these with numbers. So I can test whether 5 is equal to 5.0. That we know is true. I can test whether 5 is equal to 5.0000001, and that is false. I can test whether I can test whether 0.333333 is not equal to 1/3, which is true. All right, 0.3333, etc. is just an approximation. I can also do string comparisons, so I can compare whether hello, represented in single quotes, is the same thing as hello represented in double quotes, and indeed that is true. If I ask whether 5 is less than 10, that's true. If I ask whether hello is less than zebra, that is also true. The strings are compared lexically, one character at a time. So in this case, all that are compared are the little h at the beginning of hello and the little z at the beginning of zebra. And since z in the ASCII, that is in the UTF-8 character set, z comes after little h, this is considered to be true. If I test whether hello is less than hello with a capital H, that turns out to be false. In the ASCII character set, that is the ASCII subset of UTF-8, it turns out that all capital letters precede all lowercase letters. So little h actually comes after capital H, and consequently this comparison is false. The logical operators that I can use to combine various comparisons together are not, and or. Here again, the precedence hierarchy is different from what you might be familiar with from C or C++ or Java. Not, and or have lower precedence than all of the comparison operators. Not does have higher precedence than and, which does in turn have higher precedence than or. And I can use parentheses for grouping, that is for overriding the precedence of these operators if I wish. Now, one sort of annoying, tricky aspect of languages like C, C++, Java, and Python is that they use both the double equal symbol as an operator and the single equal symbol as an operator. My recommendation is to pronounce these operators differently. If you call both of them equals, then when you're talking about code, if you're trying to help somebody debug some code on the telephone, they may not understand which one you mean. So what I prefer to do is to call the double equal sign, let's say A gets 6. Notice that I like to call the single equal sign gets, and the double equal sign I like to call is equal to 6. Why? Well, A gets 6 is really a better description of what assignment is doing. When I say A and then a single equal sign and then 6, I'm not saying A equals 6 in the mathematical sense. I mean, mathematicians get really annoyed with programming for saying things like A gets And I can't even say it the way I mean, or the way I wish to. When you say A equals 6, to a mathematician, that's a statement that is either true or false. But in programs, of course, we who have written code are trained to understand A equals 6 means that the variable A gets the value 6. Well, I prefer to just pronounce it gets. It's short and it's meaningful. On the other hand, the double equal sign, again, rather than calling that thing equals, if you pronounce it is equal to, first of all, it's clear we're asking whether A is equal to 6. That should result in a Boolean true or false value. Is equal to is also longer than gets, and so is equal to rather than gets gives you a hint that the is equal to thing is the one that uses 2 equal signs as opposed to the gets, which just uses 1. Okay, so there's my recommendation. Use the terms gets and is equal to avoid confusion. So now that I have told you that, you can totally ignore me if you wish, but there you go. Exclamation mark equal is the not equal to test. So if I ask, and here now on slide 43, we're going to look at some combinations of comparison and logical operators. If I ask whether 4 is less than 12, that of course is true. If I ask whether 7 is greater than 2, that is also true. And so if I ask whether 4 is less than 12 and 7 is greater than 2, conceptually I certainly would want that to be true. And fortunately, the logical and does have lower precedence than the comparisons. Okay, so the implied parentheses here are around 4 less than 12 and also around 7 greater than 2. And since both of those comparisons are true, true and true is also true. Unlike languages such as C, C++, Java, in Python you can type mathematically meaningful chains of comparisons. So if I say I gets 8, we would like to be able to ask whether 4 is less than I, which in turn is less than 15. Now, in C, C++, Java, that would actually, well, it would run, but it would be a bug almost certainly, because it would compare 4 to I, resulting in true or false, and then it would compare the values true or false to 15, resulting in true. So we accidentally get the correct result if we're doing this in C or C++. But in Python, the meaning of 4 less than I less than 15 is identical to 4 less than I and I less than 15, which is what in these other languages we would have been forced to write out anyway. All right. Now, next I'm saying S gets hello, and I'm using a collection of ors here, or a sequence of ors here. If I say S is equal to hi, or S is equal to hello, or S is equal to hey, well, I didn't say so, but the logical operators are associated from left to right. Actually, so are the comparison operators. So I first compare whether S is equal to hi. Now that's false, but since I'm using an or, I then compare whether S is equal to hello. That is true. False or true is true. And because we know at this moment that S is equal to hello, and so the overall sequence of ors has to be true, it turns out that we don't even compare whether S is equal to hey. This is what's called a short circuit logical evaluation, which is similar to what happens in C or C++ or Java. And consequently, I get told that this overall sequence of ORs is true. All right, so that's now the lexical comparison examples on slide 43 I already described up here with hello versus zebra and hello with lower h versus hello with capital H. Well, now we're ready. Now that we know how to do comparisons and logic, we're ready to take a look at how to write a decision. And a simple decision consists just of the word if and then some Boolean expression. Now, some Boolean expression can be something really simple like a comparison. It can be something mindlessly simple like a Boolean value. All right. Or it can be some more complex logical test, whether expression A or expression B or expression C happens to be true. Like a function definition, the if decision ends with a colon, and then we have a compound statement, which can be one or more statements that are all at the same level of indentation. So I'm going to do something mindlessly dumb here. I'm going to say print true equals true. Or maybe I should just say true is true. Okay, so the decision evaluated this Boolean expression. Well, true is true. So consequently, the compound statement within the if is executed. This compound statement actually only had a single print statement in it. So that was very simple. If I had said, obviously, if false, print, well, since false is not true, the body of the print statement in the body is not executed. Okay, so let's do something ever so slightly more interesting. We'll say A gets 12, B gets 333. If A is less than 30, colon. Okay, now we're typing this interactively, which in real life is a little bit silly, but we're just illustrating how the if decision is written. All right, so if A is less than 30, I'm going to set B gets A. All right, so if A is less than 30, B is going to get the value of A. That's the conclusion of my if. There was only one statement, namely the assignment B gets A in the body of the if. And B is 12, okay? A was 12. 12 is certainly less than 30. So B gets the value that A refers to. Consequently, B is now referring to 12 as well. If I created a variable inside the if, that's fine. Here I'm saying if A is equal to B. Well, at this point, A is equal to B. Both of them are 12. I can say C gets minus 4. B gets A plus C. Here we have a compound statement that has multiple statements in it. And I could keep going with more statements as long as they're all indented at exactly the same level. Now, in this decision, since A is equal to B, I do set the variable C to refer to the value minus 4. And then I change B to refer to the value 12 plus minus 4, which is going to be 8. And so that was a successful decision. The compound statement in the body was executed, and B has 8 at this point. Python is immensely picky about indentation, as I have warned. So if I say C gets minus 4, and then I accidentally type a space and say B gets A plus C, well, let's see, what's happening here? Now, at this point, A is 12, B is 8, so we could argue, A is not equal to B since A is not equal to B, we should not even look at the body of the if. But Python doesn't care about, execution logic before it cares about syntax. So Python cares about syntax first. And I'm going to get yelled at here that I have unexpected indentation of that line, B gets A plus C. Now, this is seriously annoying because even if you accidentally type a space before you say something like D gets dog, you still get yelled at. So Python is just relentless about this consistency of indentation thing, and you just have to get used to it. Okay. Well, what about this indentation stuff? People have different religious positions on whether this is a good thing or a bad thing. It is a good thing in a couple of ways. First of all, almost everybody who writes Python code has code that looks like everybody else's Python code because you're more or less forced to adopt very similar indentation schemes. Also, if you are familiar with languages like C or C++ or Java or C# or what have you, you know that you have to always keep track of pairs of curly braces around the bodies of your functions, around the statements within an if decision, and so on. And by forcing this indentation rule, you don't have to worry about matching up your curly braces. On the other hand, using indentation forces you to use this clunky line continuation stuff, that is the backslash at the end of the line or parentheses around a sequence of lines. Also, these if decisions that I've written here are very short. This if decision here is only an if followed by 2 statements. What if you have an if followed by 40 statements? Now, or containing 40 statements in its body. You could complain that that's bad programming style and that you shouldn't have 40 statements within the if. And maybe that's true, maybe that's not true. But the point is, from a maintenance perspective, if you have an if and then you have 40 lines of code, it's really difficult if you're looking at, like the last 30 lines of that code on your screen. It's really difficult to notice that that code is part of an if that is 10 lines up off the top of your screen. Okay, so that's a nuisance. On the flip side, you could argue, well, this forces people not to write 40 lines of code in an if. So you win some, you lose some. There is a document called PEP8. You can just Google for PEP8. And that contains some very simple style guidelines about things like indentation, things like appropriate variable names, and the like. As Python programmers, we simply have to live with this requirement for indentation and the lack of something like curly braces to begin and end our functions, to begin and end our ifs, and so on. The general form of an if-else decision is shown here on slide 50. We have to have one if part followed by a Boolean expression ending with a colon, and then a compound statement consisting of at least one statement and perhaps many more than that. Then optionally, we can have some sequence of elif parts. Now, elif is simply an abbreviation for else if, of course. And the idea here is that we can test a secondary Boolean expression. So if the Boolean expression for the if was false, we can test whether the Boolean expression for the first elif is true. If not, we can drop down to another elif and so forth. We can have as many of these elifs as we wish. And at the very bottom, also optionally, we're allowed to have at most one else. So if all of the Boolean expressions for the if and all of the elifs associated with the if are false, then we're going to drop down to else and execute the compound statement contained within else. Okay, now we're going to take a look at a form of loop that Python provides. There are other forms of loop, but since we've talked about comparison operators and Boolean expressions, we're going to first discuss the while loop. The idea here is while some Boolean expression is true, and notice that the while line has a colon on the end, just like the if and just like a function definition. So while that Boolean expression is true, we are going to execute the compound statement contained within the body of that while loop. Let me just do a quick example of that. So if I say, of course I want to be careful not to write an infinite loop. If I say while true, that's going to be an infinite loop, which is going to end up doing some function, some sequence of statements forever. But let me do something like this. If I say I gets 0, and while I is less than 10, let's print I as a string and i's value, and let's also modify I to I plus 1. Okay, so this is a very conventional while loop that initializes, in which we have initialized the variable I. We're then testing the value of I to make sure that it's less than 10. Then we're doing something with I, in this case simply printing it out. And then we're modifying I, and hopefully we've done this in such a way that this is not an infinite loop. And indeed, yes. So we get told I is 0, I is 1, up through I is 9. All right, so that's a very simple while loop. We've dealt with assignment already. We've said things like A gets 123, B gets 12. It turns out that Python supports something called multiple assignment that allows you to say things like I, j, k gets, and then an equivalent number of values on the right side of the equal sign, 1, 2, 3. These three values on the right, 1, 2, 3, are assigned into the variables, the corresponding variables on the left. So I now has a value of 1, j refers to 2, k refers to 3. One situation where you're going to see multiple assignment frequently, especially in things like sorting algorithms and so on, is it's possible to simply swap the values of two variables, j and k, let's say, by saying j, k gets k, j. Now, the values on the right-hand side are determined first, and those values then become the new values of the two variables on the left-hand side. So we don't have a situation here where we're assigning the value of k into j, then we're assigning that new value of j into k. What we're doing is we're grabbing the original value of k, which at this point is 3, and the original value of j, which at this point is 2, and those are going to become the new values of j and k. So we will have swapped. J now contains 3, k now contains 2. It's necessary to have exactly the same number of variable names on the left side as you have values on the right side. If I have 3 variables, x, y, z, but only 2 values, then I get yelled at. As a convenience, rather than having to say things like A get, well, let's see, do we have an A? Yes, we do. A is 123. Rather than saying A gets A plus 1, Python provides a bunch of assignment operators, very similar to those in C, C++, Java. I can say A plus gets 1. That's simply an abbreviation for saying A gets A plus 1. Likewise, I can say A times gets 2, let's say. and that will double 2. If I say a divide gets 3, we're doing a division, so a is not going to be an int when we're done with this. A is going to be a float. Even if the fraction part had been 0, a would still be a float. Right? So if I say a gets 250 and then a divide gets 5, this is not going to be 50. This is going to be 50.0. All right, and so forth. So those are just for convenience, but they're very commonly used. Let's combine some of these things we've just introduced to create a factorial function that computes n factorial. And I want a program file for this. I don't want to type in this factorial function definition in my interactive shell. So let me return to my editor. Let me save fun test, just to be careful. And now I'm going to type in this factorial test program. And as before, I'm not going to require you to watch me type. So I'm going to start typing. And now I'm just finishing up this function. And I will save as, I don't want to accidentally overwrite fun test. I'm going to call this fact test. And the editor will add a .py. All right, so this is a naive function that computes the factorial of some integer argument. And if I add some print statements, again, I won't require you to watch me type, so I'm going to type these guys in. All right, and so now I've just about got these test conditions, or these tests of the function typed in. And when I run this program, okay, I want to save it first before I run it. If I try to run it now without having saved it, I get told source must be saved. Okay to save, and I'm going to say okay, and that will save it for me and then run it. And notice the output that I get. So my code correctly says that 0 factorial is 1, 1 factorial is 1, 3 factorial is 3 times 2 is 6, 9 factorial, which I can't do in my head, is 362,880, and then 100 factorial is this big number. Because we have arbitrary precision integers in Python, these numbers are completely correct. Let's look back at the program. So what are we doing here? Well, first of all, I've defined factorial of n as my function name, and I need to return a value from this thing when I'm all done. Now, the default return value, if n is 0, is going to be 1. So I'll set 1 as my initial return value. I also need a counter variable, which is going to count from 1 up to n, and that also I'm initializing with 1. All right, I'm doing this in a loop, specifically a while loop. So while I is less than or equal to n, well, let's see. If n is 0, then while 1 is less than or equal to n, that's going to fail immediately, and I'll simply drop down to the return statement and return the 1, which is the initial value of ret. Similarly, let's suppose that n comes in as 1. Okay, so ret is 1, I is 1, and while I is less than or equal to 1, I'm going to multiply ret by I, so I get 1 times 1 is 1. I increment I by 1, and now the loop terminates, and I return ret, which is 1. Let's suppose that factorial is 3. Okay, so the initial ret value is 1, the initial counter value is 1, and I'm saying while I is less than or equal to 3, ret times gets I. So 1 is going to become 1 times 1 is 1. and I is going to become 2. Well, 2 is still less than or equal to 3, so 1 is now going to become 1 times 2 is 2, and I is going to become 3. 3 is still less than or equal to 3, so ret is going to become 2 times 3 is 6, and I is going to become 4. Now at that point the loop is done, and I return the 6 that I've computed. And we can continue this idea. So although I haven't exactly mathematically proven this, I hope you're persuaded that this algorithm does work and will give me back the correct value for factorials of positive integers, non-negative integers, n. Now, we do have some problems. If I attempt to compute the factorial of a negative, that's going to be a problem. By the way, since I have run this module, the factorial function continues to be available to me now in this interactive shell. So I can say print the factorial of -5. Now that shouldn't work, and I get the default of 1. Okay, perhaps I should get an error message instead of the default of 1. Likewise, if I ask to print factorial of 1.5, my factorial function doesn't handle arbitrary real numbers. Once again, I get back 1 sort of by accident. And certainly my factorial function is not smart enough to handle strings, even if the string, like 6, makes sense to human beings as a number. Okay, so here I get yelled at. If I look back at my program, n is coming in as the string 6, and at this point here I'm asking whether the int 1 is less than or equal to the string SIX. That's simply not a valid comparison, so I get told that that less than or equal sign is not supported for comparing an int to a str. All right, so in order to make our function robust, we can do one of two things. The cheap thing to do is to document how the user is supposed to use the function, and if the user uses the function the wrong way, to just shrug and say, well, the user is stupid, the user deserves what they get. But let's be a little more careful and kind than that. And what we'll do is we'll put in some checks, first of all, to make sure that the data type that's been passed in is int. Type is a built-in function that will tell you the data type of some value. So if the type of the value that comes in is not int, or if the value of n itself is less than 0, we're going to display an error message and return the special value none to indicate that the function did not compute and return a correct int value. All right, so this correction, this fix to our function will then prevent these kinds of mistakes. So let me hammer this in. Okay, so I've just about got this typed in. And notice that so that we have both versions of this factorial function available, I'm going to save this version into the file name facttest2.py. So we now have both versions, the naive version and the safer version of this factorial function. All right, so now if I have these tests that we know shouldn't work, now I will get error messages rather than just I will get appropriate error messages telling me what I should have done rather than just getting garbage and Python errors. All right, so let me save this and run it. And there we go. Okay, so I get the good output for the values 0, 139, and 100 factorial. And then I get these error messages. Minus 5 has to be an integer greater than or equal to 0, likewise 1.5, likewise 6. So that's a little better. Okay, and I just showed that. So we've been writing our own modules, prog1, fun test, fact test, and fact test 1. It turns out that there are several standard modules and several add-on modules that you can simply use in your programs to provide things like mathematical functions, string manipulation, web access, vectors and matrices, spreadsheets, and that kind of thing. One of the simplest ones of these is the math module that provides sort of ordinary number manipulation functions like ceiling, floor, absolute value, exponential and log functions, trig functions like sine and cosine, error function and the gamma function, and some other things having to do with computing distributions, constants like a value for pi and a value for e, and so on. So let's see how we can make use of this predefined stuff so that we don't have to write these things ourselves. All right, well, I'm going to create a file called math test now. Let me make sure that I have saved fact test 2, and now I'm going to create math test. And I'll get back to you later. And let's take a look at what we've done here. Now, I want to be able to use these math library, these math module facilities. And in order to get access to them, I'm saying import math. Math is a built-in module, so I can gain access to all its facilities by simply saying import math. And then, in order to access individual functions or values within that math module, I prefix the function or the value that I want with math dot. So math.exp is basically the e to the x function that's defined in the math module. Here I'm computing e to the 0, which had better be 1, e to the 1, which had better be e, and e to the minus 1, which is 1 over e. And those ought to be sort of recognizable values. Math.pi should be recognizable. Now, the cosine of pi is minus 1 if your trig is up to speed. On the other hand, the cosine of pi over 2 is 0. So I ought to get the value for pi and then minus 1 and then 0 for these cosines. Ceiling and floor give you the next higher int and the next lower int, respectively. And let's see what we get. Now, I had better save this as math test, and now I can run it. There we go. So e to the 0 is 1.0. That's good. E to the 1 is e, 2.71828, etc., etc. And of course, that's only good out to 16 or 17 digits. And here we have 1 over e, which again is only good out to a finite number of digits. Now for the cosines, first of all, this is a good value for pi, 3.1415926, etc. And I do get minus 1.0 as the cosine of pi. Now, I almost get 0 for the cosine of pi over 2, but we run into this round-off problem again. I don't get exactly 0. I just get something that's really, really, really close to 0. 6 times 10 to the minus 17th power. So beware of thinking of this round-off as some meaningful number. Okay, so the ceiling of 2.7 is the integer 3, and the floor of 2.7 is the integer 2. All right. Now, it's painful to have to type math dot in front of each one of these values that I want to use or each one of these functions that I want to call. So here's an improvement. What is most often done with the math module is we say import math as M. So as allows me to specify an alternate name or an abbreviated name for accessing things in the math module. And obviously in my code, as you can see in the 3 print statements on slide 62 here, it's going to be much easier for me to type m.exp, m.pi, m.cosine, etc. So we get the same result there, it's just less typing to do. Finally, if I wish to avoid having to type math dot or m dot altogether, I can say something like from math, import the individual functions that I want to be able to use directly. And now those just become top-level functions in my program's so-called namespace, and I can just call them directly without a math dot or without an m dot in front of them. So those are 3 different progressively more convenient mechanisms for using things from the math module. All right, well, we have reached the end of the first week lectures. We introduced basic Python types and values. We talked about variables and assignments. We looked at arithmetic operations and comparison and logical operators. We took a look at the if, elif, else decision and the while loop. There's another form of loop that we're going to see in the next lecture, but while is all we need for the moment. And we took a look at some very simple functions that expect to receive parameters and that either may or may not return values. If a function does not explicitly return a value, then what you get is none by default. We did talk about several of Python's low-level data types, but we did not, and we will not, in fact, in this prep course, get into talking about our own classes, perhaps using inheritance, and perhaps using polymorphism. Finally, we did talk about how to use the idle editor in order to put Python code in a program file, and how we can then execute that file, and also how we can import modules such as the math module to make use of other modules' facilities. All right, so obviously we've left out a tremendous amount, but once you have numbers and strings, arithmetic, comparison and logic, decisions and loops, functions, and the ability to write programs, you actually can get useful stuff accomplished even with just this little bit of stuff we've talked about so far. So we will continue with more good stuff in week 2.